Hi. I'm honored to have the opportunity to address both Splash and eCoop with this talk, and to accept the Del Nygaard Jr. Prize. In this talk, I will describe some of the research projects that were mentioned in my award citation, and go into the story behind each of these projects. But before going to the story that brought me here, I'd like to start off with what I think is a nice story that describes my research philosophy. So speaking to a room full of computer scientists, I don't think that it should be that necessary for me to underscore the importance of software in our lives. But perhaps you will humor me for just a moment because it is nonetheless true. For instance, we rely on computer software for the critical infrastructure that maintains our transportation, power, and financial systems. But also now more than ever, our lives literally rely on software. Not just for this critical cyber infrastructure that underpins our entire financial and world systems, but also for simple everyday interactions. In order to see our friends, our family, our students, our classmates, we now turn to software. Never before has software played a more critical role in our lives. And yet, with our increasing reliance on software, a simple software bug introduced by a developer who's rushed to meet a deadline can result in an even more stressful first day of class for students all over the world returning from a chaotic summer break when on August 24th, Zoom was unavailable for users all over the East Coast and Europe. First day of class for many schools in the US also happened to be the first day of ICFP, which I had volunteered to help virtualize. It's not a very fun morning. But more broadly, systems outages affect all of us. Consider, for instance, a 2019 outage of Facebook, WhatsApp, and Instagram that was sufficiently impactful to make headlines, and an outage of Amazon's S3 service that was covered by many news outlets as the outage that broke the internet, taking down sites like Coursera, Medium, Slack, Docker, Expedia, and many more. Bugs that cause outages are one thing, but even worse are vulnerabilities, as was the case in the 2017 Equifax data breach that impacted most Americans and pretty much any foreigner who had a social security number. This breach is currently projected to cost Equifax over $660 million, plus another $600 million in security education and awareness expenses. It'll be quite a while before this is out of the headlines, with ongoing investigations into the hackers allegedly responsible. Now, in the aftermath of high-profile incidents like this, the first question is always, what went wrong? Followed by, what can we do better next time? It is by far easiest to simply blame the developers, since after all, we all know that apps are just simply never tested enough. But how do we fix this? Do we do more testing? What about Equifax? A patch that would have prevented this exploit was available for months and was not applied. Why wasn't it applied? Well, the Federal Trade Commission report from this past January noted that, among other things, that Equifax didn't have a sufficient risk-based testing program. Okay, so probably we do need to be testing more. Do we just, try harder to write more secure and bug-free code? Or do we hire more testers and spend more time testing and hope that that works out? Well, I think we really can't just go out there and hire more testers. In fact, I don't think it's going to be that easy to go out there and hire more tech workers of any kind. According to the U.S. Department of Labor, there are over 500,000 computing-related job openings right now, and they project that by 2026, there will be over 3.5 million computing-related job openings. Even though we're investing heavily in training our workforce for these jobs, we'll surely fall short of demand. For instance, the state of Virginia promised $1 billion to local computer science programs, including over $125 million to my former institution. But still, money doesn't solve everything, because even if you can find the money, find the students, how do you even find enough faculty to be prepared for such a tidal wave of newcomers? So if we can't get more testers, instead, we need to find a way to find more bugs and vulnerabilities with fewer human hours. What we need is a force multiplier, something that will take a single hour of a developer's quality assurance efforts and result in quality software that otherwise might have taken that same developer, say, 10 hours to get right. Moreover, we need to design tooling that does not require specialized intensive training. In fact, I believe that we need something that even casual developers of open source projects can use, since so many large projects rely on open source components. While I've had industrial collaborations, I evaluate much of my research on open source projects, and also make contributions back to the community by releasing my tools as open source and fixing bugs in popular open source projects that I use along the way, like Apache Maven and the Pit mutation framework. And supporting open source projects also helps support industry. A recent audit of 1,200 proprietary codebases found that literally 99% of them use open source components. And worse, how are these open source components used? To some degree, this might be fairly safe. These proprietary projects might be built on top of, say, commodity infrastructure that's really well supported by major vendors like Linux. Many major software vendors support Linux by finding and patching vulnerabilities in it, and hopefully we can trust that this operating system is safe. However, it's increasingly common that if you're building a large proprietary app, we don't just have all of this proprietary code that we wrote that's running on top of Linux, but instead, we have this very tall development stack with middleware like struts or Django, which include an enormous amount of functionality, making it really easy for developers to stand up complicated applications very quickly. But it also can increase our attack surface. And this is for sure representative of the software stack that was used by Equifax that was exploited, where the vulnerability was in struts. So my work applies software testing and program analysis ideas to develop new tools that can act as this force multiplier for developers' time. I focus on a task that developers already have, like software testing, identify pain points, and then design new interventions to make those tasks easier. While some of my research focuses on core testing challenges, such as the test oracle problem, or on core analysis problems like dynamic taint tracking, much of my most recent and exciting research leverages contributions from both of these fields. All of my work has targeted object-oriented languages, typically Java. The two projects that I'll talk about today both are aimed at reducing false alarms. That is, reducing the number of occasions that a tool tells a developer, go fix this bug that I found, when there is not in fact a bug. By reducing time that developers spend tracking down false alarms, we can allow them to focus more on what they do best. The first kind of false alarm that I'll talk about are flaky tests, which are tests that can pass or fail non-deterministically. Formulated more precisely, a flaky test is a test case that can both pass and fail without any change to the code being tested. Flaky tests can be a significant nuisance to developers because they effectively generate these false alarms, saying, a change that you recently made broke this test, go fix your change, when in fact, the test isn't actually failing due to the change, but due to some of these external non-determinism sources. To some extent, flaky tests have always existed, but with the development of continuous integration technologies and the growing complexity of the software that we're testing, they're becoming more and more distracting for developers. Google reports that 16% of their automated tests are flaky, and Microsoft reports 5% of the test failures in their Windows and Dynamics projects are flaky. In fact, most developers experience flaky tests and find them to be a nuisance. I've been working in this flaky test space since 2014 and have developed approaches and tools to help developers detect, prevent, and mitigate the effect of flakiness on their testing activities so that they can focus on tests that are truly failing due to bugs that they've introduced rather than due to these non-deterministic sources. Flaky tests is an area that I'm still quite active in, and my collaborator Wing Lam will present our most recent work on investigating the origin of flaky tests at OOPS-Led this coming week. I'd like to go back to the beginning, though, to the very first flaky test problem that I considered, which was test case dependencies. Test case dependencies occur when we write tests that we assume can run in any order. So I have these tests 1, 2, 3, 4, I run them and they all pass. But then perhaps we reorder the tests, and when run in this different order, they do not have the same behavior. Instead, now we might see that a test that had just passed now failed. This phenomena is called a test order dependency because the outcome of one test depends on the order that it's run in the suite. As developers write new tests and run them in different ways, these tests can unexpectedly fail. They're flaky. Okay, so how can tests become dependent on each other? Here's a code snippet from the Apache Tomcat application server. It shows a configuration variable for the server that defines whether the server should allow an unescaped equal sign in a cookie value. We have here a static field with its initializer. So static fields, Java, these are global variables. They're owned by classes, not objects. And hence this initializer that sets the field is only going to run once when the class that owns this the class that declares this field is initialized. Note that this initializer reads a system property, which is pretty much the equivalent of reading an environmental variable. So what happens? Well, let's take a look at the tail of these two tests. Test allow equals in value and test don't allow equals in value. The first test will set the environmental variable to true, start Tomcat, and run the test. When this test is run on its own, or run as the first test, this test will pass. The second test will check the behavior when this environmental variable is set to false. So it will set this environmental variable to false, start Tomcat, and run the test. However, if this test runs in the same JVM as the prior test, which initialized this property to true, setting this static field to true, this test is now going to fail, because the test assumes that by setting the environmental variable to false, that will change the value of this static field, but in fact it won't. This static field will only get set when this class is loaded. Note that we have the same problem if we run the tests in the opposite order. Only one of these tests can pass if they run in the same process. So for this reason, we found that many developers isolated their test cases, so that for an entire test suite that contains many tests like this, each test will run in its own JVM. So running a test will mean starting a new JVM, running a test method, and then tearing down that JVM. Back when we performed this work in 2014, we found that this test isolation step added an overhead of about 1.5 seconds, which included the time to start up a new process, load in the JVM, load in all of the required classes, both for the JVM and also for the system that we're testing, and perform this initialization. This overhead can be absolutely immense when you consider the overall time that it takes to run some of these tests. We looked at cases where unit tests were just 3 to 5 milliseconds long, in which case this fairly constant but much larger JVM startup time totally dominates testing time, forcing developers to wait longer to get testing results, or alternatively running their tests without isolation, but perhaps with unexpected failures. So our goal with VMVM was to avoid this overhead by running all of the tests in one process, but with each test still getting the same level of isolation as if it were still running in its own process. We get the speed of running them in the same process without the risk of these flaky tests. So we took this idea and implemented our tool that isolates these in-memory side effects just like restarting the JVM. A key design goal that I clung to in building this was to ensure that it would be easy for developers to include in their existing automated testing pipelines. Something that required a custom JVM implementation or required access to source code for all third-party libraries would be, in my opinion, useless to the developers that I was targeting. This is tricky to implement because each static field might have some dynamically computed starting value, and hence you can't just reset fields to the initial value that they had before your test ran, but you really need to literally trigger the same initialization semantics that the JVM would do when it loads the class for the first time. I'll step through very briefly how VMVM works. VMVM works through bytecode instrumentation, using a few clever tricks to optimize its performance in the JVM. I'll show this at the level of source code, but note that VMVM works entirely with bytecode instrumentation and doesn't touch or require source code. VMVM adds a new field to each class, which is used to keep track of its reinitialization status, along with a reset method, which acquires the appropriate monitor, checks if reinitialization is needed, and then, if needed, optionally calls some reset method that will trigger the same class initialization method that the JVM would at startup. I also add a check and reinit method, which performs a racy unsynchronized check on that same static field, and optionally calls the reset method. Breaking up the initialization check like this significantly improves JIT optimizations because it enables the check to be easily inlined. Then, immediately before any instruction that would potentially trigger initialization, like in this case, a read of this field data of this class 2, VMVM simply inserts a call to that same check and reinit function. There are also some rough edges here that I've glossed over, mainly because of the JVM semantics for resolving static fields are slightly different than those for resolving static methods. Now, this first foray into Java bytecode instrumentation really set me down a long road of developing different runtime support tools for the JVM that I'll get to in a few minutes in this talk. How did VMVM work? Well, I show here the relative speedup that was afforded by VMVM in comparison to this traditionally isolated test suite execution, where each test class ran in its own JVM. The speedup from VMVM was directly related to the number and speed of each test. In the extreme cases where there were a lot of very fast tests, like this UPM example, VMVM had a huge speedup, while in the other extreme, with very few very slow tests, like this bristlecone subject, VMVM had no speedup, because remember that what it was doing was reducing the time spent between tests. If you have lots of fast tests, you can get a big improvement. If you have fewer slow tests, it doesn't really do much. So what happened next? In February of 2014, just after the acceptance for this paper was announced, but long before the conference, I was invited to attend a release engineering workshop and bring a poster describing this work to a workshop that was being held at Google. This was a really cool workshop. Being held at Google, it attracted many industry practitioners who might be less likely to travel to a conference in another country, but perhaps they could be lured just out to Google's Mountain View campus. So I went to this workshop, and I'll say it was probably going to be many years from now before we're bringing our mouths so close to the Android sculptures there, but it was a great time. I presented my poster that summarized the work that I just displayed on improving test suite execution time by reducing the time spent doing this isolation. And someone who happened to walk up and chat with me about the poster was this guy Mohan, who was the product manager for a makefile acceleration tool at a company called ELECTRICCLOUD. It turned out that he was at the workshop talking about some continuous deployment stuff, but his group was also looking for an approach to specifically accelerate Java builds. They had been doing work accelerating makefile-based builds, where they found that there were lots of different tasks that they could parallelize to make run faster. But Java builds were slow and they were having difficulty accelerating them because of their really slow running tests. So Gail and I started a collaboration with Mohan and also the lead engineer on the project inside of ELECTRICCLOUD, Eric. So we did some science and confirmed empirically that in open source projects, what their industrial clients at ELECTRICCLOUD had been seeing. Not shockingly, testing takes by far the majority of time in Java projects. This pie looked quite different from legacy make-based projects. Then we built some complicated machinery to let us track the data dependencies between each test, letting us parallelize them safely and efficiently. So we could identify that if we wanted to run our tests in an order that would be fast and also safe, we could track which tests had to run before which other tests, which tests couldn't run before other tests, and then create a safe parallel schedule. This appeared at FSE 2015 in our joint paper. My advice to you here, if you have the opportunity to participate in a workshop that focuses on problems that you are interested in or similar, you should go. This connection was really cool, and it definitely wouldn't have happened otherwise had I not been at this workshop. Okay. So that was the start of my work on test order dependencies and flaky tests. A few years later, Alessio reached out to me because he was interested in refining that data dependency graph that Electric Test built in order to include only edges that were necessary to enforce for test outcomes. Since some of those dependencies could be benign, Electric Test would be over-approximating the number of dependencies that needed to be enforced. This topic of test order dependencies came up again just this past year. Working with Milos and his students and an undergrad of mine at Mason, we debugged just why Maven's built-in test isolation was so bad. We did some profiling and found that in Maven, the amount of time spent shutting down a JVM after you ran a test in isolation was enormous. This is not even considering how long it takes to start up this JVM and load in the test cases. This is literally just the time for the JVM to shut down. So we looked into this closer, found a bug that was specific to Maven. Very interestingly, when we had evaluated VMVM 6 years before this, we had looked mostly at these ant-based projects that didn't have this weird behavior that Maven was seeing. So we were totally oblivious at the time to what was happening in Maven. But we fixed this bug in Maven, which happened to be there since basically the origin of Maven. It had been caused by some very inefficient I/O stream handling. We dramatically improved the performance of test isolation in Maven for all developers, regardless of whether they were using VMVM or something like it. Got this change merged into Maven, and wrote up an experience report describing the whole thing. Well, prior test order dependency work of mine resulted in papers. I felt that this was the first outcome that really made a broad impact on developers. Developers didn't need to adopt my tool to benefit from this. Instead, they just had to be using Maven. All of this test order dependency work also brought me into many close collaborations with Darko Marinov and his students on flaky tests, like detecting flaky tests, regardless of the cause of that flakiness. Not just looking at test order dependencies, but also looking more broadly at different sources like thread scheduling or asynchronous task racing. We also looked at approaches to mitigate the effect of flakiness on mutation tests, and also on studying the origins of flaky tests and how they come about. So this is the story of all of this test order dependency and flaky test work that I see looking backwards. From today, this privileged position where the work has been done, can try to, build up a story that connects it. But this is by no means where I thought this work was going to go. So I was putting together this talk and trying to decide what I would have wanted to see if I were me, 10 years ago, a PhD student just starting out, watching this talk. For sure I know that I would have doubted that I would ever be giving this talk. When I was starting out, I had no idea what I wanted to do or how, and in retrospect, I feel like I stumbled through a lot of it. So I want to tell a different story now, one that starts not with an ICSE distinguished paper, but one that starts with an undergraduate research project. And I assure you, we are going to get back to test isolation. So I started out as an undergraduate doing some undergraduate project work with a professor at Columbia, Gail Kaiser, who would eventually become my PhD advisor. The project was called GenSpace. GenSpace was an effort to add community features to a systems biology research toolkit that was called GE Workbench. This was the first project that I worked on in any sort of research capacity, and was a project that funded the first few years of my PhD. It was a project that I found extremely fascinating, but honestly, I didn't really want to do it. While I was really interested in the various ways to design new computer-based interactions to help scientists work together and collaboratively, even if they're remotely distributed, the parts of this project that really interested me most were like the systems hacking parts, and less so the human-facing parts. So at the same time that I was working on GenSpace, there was another project in the lab going on that was much more systemsy. The way that I remember it, Gail suggested that I take a look at some of the more recent papers that her student, Chris Murphy, who was just finishing his PhD at the time, had written on these topics of in vivo and metamorphic testing. So I did. In vivo testing is this cool idea for creating what are effectively extended runtime checked assertions. Runtime checked assertions allow us to write guards in our code to enforce specific properties at runtime. If a parameter is null, fail your assertion. Easy. In vivo testing takes that idea much further, allowing an entire test case that might have side effects to be embedded in that assertion. So to do this, when an in vivo test site is reached, like where you have one of these assertions, you make a decision. Should I run an in vivo test, or should I just let the program behave normally? If the program behaves normally, you just continue off with your execution as it was. But if you think that this state is interesting, and that the values that are being passed into this method could be interesting to be passed into some test case that might have some side effects, you now run that test case in a separate process. You fork your execution, have this other execution, you manipulate the input to this function and say, let's give it something else in this test, what I observed at runtime. So I didn't really know at the time how to articulate my research philosophy on systems at the time, but I read this paper and there was this one sentence that really stood out to me. as invite, which was the name of the framework that Chris had built, is currently implemented in Java, and there's no fork in Java, we used a JNI call to a simple native C program which executes the fork. I read this sentence, and having been in the middle of an operating systems class at the time, recognized some implications here. This meant that this approach, this tool, could never really work with multi-threaded programs. It would eventually crash most JVMs, because even if the application running in the JVM is single-threaded, the JVM itself will still have garbage collector thread, JIT compilation threads, and this behavior could start to diverge between the fork and the original program. So this became my singular mission, not focusing on this concept of an in vivo test and what to do with this idea of having tests that run in parallel with an application, but instead, how could I make this diagram work, but without using fork? And that kind of became my mission at the time. So I spent the first few years of my PhD working primarily on GenSpace, but in my spare time I was hacking on this Java stuff to try to come up with some way to isolate those in vivo test case executions from the program execution. The first time I wrote this up, we tried to send it to a workshop on security testing. And I will share, we got some pretty harsh reviews, especially given that it was a short workshop paper. So I was stumped and not really sure what I wanted to do with this work. But at the time, this GenSpace work that I had been pushing simultaneously was also meandering into a new project with another student in the lab, Swap, who was interested in CS education. So later that same year, I went to ESEC-FSE to present a short paper that was describing some new ideas that we had for gamification and software testing at this great workshop on social software engineering. Now in 2011, ESEC-FSE was held in Szeged, a lovely city along a river in the south of Hungary. It's about a 2-hour drive from the nearest airport in Budapest. And the easiest way to make the 2-hour trip was by motor coaches that were arranged by the conference organizers. On the drive down to Szeged, I sat next to another PhD student from the University of Washington, Kavanch, who happened to also be on his way to present a new ideas paper called Finding Bugs by Isolating Unit Tests. And we made a bit of casual conversation, and then I think we both went to sleep. This was the first time that I had heard about this problem of test dependencies. I later, back in my hotel room, read his paper and saw a line in it which mentioned that this test isolation process created considerable overhead. I had this weird isolation thing that I couldn't quite figure out how to make work for in vivo testing, and here was a problem that literally required an efficient way to isolate tests. And then from this, I had this idea, we put together VRUM. This led to my PhD thesis, basically all of the work that I just presented on flaky tests, an SF grant, and many collaborations. So, in retrospect, I think that I really have to say that at the time, crammed into this minibus, first time ever in Europe, first time having a red-eye flight, making small talk with the person next to you when you're super jet-lagged and confused and far from home was a bit of a struggle for me. Not just, small talk about being tired, but also small talk about research. This was not something that was very exciting to me. This was not something that I really wanted to do, but something that I'm extremely pleased that over those 2 hours I happened to have, a 1-minute conversation. So, advice to 10-year-ago me, or maybe some of you watching this, ask people what they're working on. Tell them what you're working on. Ask them where they are from. Tell them where you are from. Research is an incredibly social process. The reason we come to conferences is not just to see a bunch of presentations. It's to see our colleagues and to meet new ones. I recognize that at a virtual conference, you don't get this fun, let's say, captive networking experience, being trapped in a minibus sitting next to someone. But think of it like this. You can use this experience of being at this virtual conference to talk to anyone at this conference, even if they're not sitting next to you in the minibus or even physically in the same place. Okay, still not done with this in vivo testing story though. So I had also started working part-time on a project with a new distributed systems professor at Columbia, Roxana, along with her new student and some visiting students. This project went through many names and many twists. Originally we called it ENCOS, then we called it LOS, and ultimately we called it Pebbles, and it was published at OSDI in 2014. Pebbles was an extremely complex hack on top of Android, which provided system-level privacy abstractions that were user context sensitive. So, before Pebbles, the data protection that an operating system could provide was maybe all or nothing, where your entire device was encrypted, or none of it was. Or perhaps the operating system could provide some per-application encryption, where some apps and their data were encrypted and others were not. But our idea with Pebbles was to focus on this idea of user-level logical data objects. Like if we just drilled into the email application and talked about emails. We don't want to have necessarily all of our emails protected the same way, but likely we want to have some different categories of emails, like assigning emails to contexts like personal emails and business emails. We want to have different privacy and security standards for each. So what Pebbles did was take this idea of data privacy contexts and automatically protect data in your Android apps in these contexts, without requiring the user or the app developer to tell the operating system how some piece of data, like an email, was actually represented. Pebbles literally tracked from user tapping on the screen on an email shown in a list to all of the places on the device where that thing was stored in its relationships. That we could see if you touch on the subject of an email, you're referring to actually some row in a SQLite table, plus also a few rows in another SQLite table that might be related, say attachments, maybe some web view cache files if that email was ever viewed, really anything that relates to it. Then we would do privacy, encryption, auditing, all these kinds of great stuff at the level of these logical data objects. So this was an extremely long and complex project, and perhaps the one part that really stood out most to me and was most fascinated by was this dynamic analysis that underpinned this entire system and made it work, which was dynamic taint tracking. So while we were wrapping up Pebbles and tending to its repeated rejections, renaming, and resubmissions that can be, unfortunately, so typical of systems research, I took what I had learned from Taintroid, which was the amazing taint tracking tool that we used to make Pebbles work, and I built PHOSPHOR, which is a dynamic taint tracking tool for the JVM that works with any Java code and on any JVM. But I promised to return to in-vivo testing, not just for a long rant on JVM instrumentation tools. So when I presented PHOSPHOR at UPSLA in 2014, I still hadn't quite figured out yet the test dependency story fully. And I was still very interested in this in-vivo testing runtime isolation idea. The very next paper in the session was also happened to be a large complex JVM instrumentation tool. This one for dynamically applying patches to code running in the JVM. It was presented by Luis Pina, who at the time, like me, was also a PhD student. Luis and I chatted a lot later that day after our talks. I was very interested to hear how he thought the in-vivo testing scheme could be implemented more cleanly, and we saw each other a few more times over the coming years at different conferences. Shortly after I became an assistant professor at George Mason, Luis was looking for a postdoctoral position in the same geographic area, and we were able to work something out. Shortly after, we built Crochet together, which was basically the system that I set out wanting to build from the start nearly 10 years ago, which allowed for this very fine-grained, fast micro-checkpoint and rollback in a JVM. Useful for many things, not just in vivo test isolation. Since then, others have come along and used Crochet to build out the entire in vivo testing approach for the JVM. It's very cool work. Ultimately, what I wanted to do with Crochet was put it together with PHOSPHOR in some way to do guided input generation, but we haven't quite gotten there yet. But I have had the chance to find other applications for PHOSPHOR. So, taint tracking, the analysis that PHOSPHOR implements, is a commonly used analysis for detecting and defending against code injection vulnerabilities, like the vulnerability that was exploited in the attack on Equifax. Dynamic taint tracking tools like PHOSPHOR can be used to defend against code injection attacks by detecting them just in time, allowing a system to automatically defend itself against malicious inputs by recognizing them. However, even a super optimized dynamic taint tracking tool is going to be too slow to deploy in most production environments. On the other hand, static taint tracking tools can be used before deployment to audit code for injection vulnerabilities, but these tools are prone to false positives, generating perhaps hundreds of false alarms for a developer to go investigate. They also do not guarantee detection of all security injection vulnerabilities. So our solution reduces developer time tracking down those false alarms from this analysis. Our solution combines both testing and analysis in an approach that quite literally acts as a force multiplier for developers' time, that we call RIVULET, which reveals injection vulnerabilities by leveraging existing tests and analysis. RIVULET assumes that developers have followed best practices, that they've created automated test suites that check for functional correctness, but we do not assume that they check for any security properties. For instance, a developer of an electronic health system might have created a test for a feature that can be used to send a message to a healthcare provider. This test might consist of steps like logging into this app as a patient, entering sample telemedicine data, and then submitting a message to the healthcare provider. Then, as a good functional test, it will have some assertions to check to make sure that the message was sent successfully. This is an extremely complicated workflow for a purely automated testing tool to detect and go through, since there are many specific values that must be entered in order to trigger the workflow and satisfy various validation criteria. RIVULET's approach is to amplify this test, to take the test that developers already took the time to write, and use an embedded analysis to detect that perhaps this last component is the one that's vulnerable to code injection attacks, and then RIVULET generates exploit scripts based on this existing functional test case to demonstrate the vulnerability to the developer. RIVULET detects vulnerabilities by combining taint tracking with testing in a way that actually could really be seen as in-vivo testing for security purposes. First, RIVULET detects candidate tests that might be used to detect security vulnerabilities by executing each of the original developer-provided tests using dynamic taint tracking. As the test runs, RIVULET intercepts each HTTP request as it arrives in the application server. It taints the components of the request, and then when data arrives at a potentially vulnerable sync location, like the one that could execute code, RIVULET inspects the taint tags on those values to identify which, if any, of the user-controlled inputs flowed to it. In this case, we found that a cookie header was detected as flowing back to the user through an HTTP response, which could be exploited in a cross-site scripting attack. Then for each one of these candidate tests, RIVULET cleverly reruns them, effectively performing in-vivo testing on the tests by modifying the values supplied by each test case. In this case, RIVULET would change that session ID variable to use an attack string. The modified test is again executed with taint tracking, and this time, if the new malicious value flows into a sink where it could be used in an attack, RIVULET examines the entire response in order to determine if an attack really occurred. This step is important because simply seeing data flowing into a vulnerable method does not imply an attack. In this example here, that could be representative of a cross-site scripting attack, there actually is no true vulnerability because even though RIVULET succeeded in getting the attack string passed into the browser, we can see that this string is in fact included in a comment and therefore will not execute. When RIVULET eventually does generate an input that does reveal the attack, like for instance, if it broke out of that comment string, then RIVULET simply marks this vulnerability as confirmed and creates a reproduction script so that developers can directly run this test with this modified input. We evaluated RIVULET on a number of standard benchmarks for code injection vulnerability testing, as well as on some open source projects. We observed only a single false negative from RIVULET, but 9 false negatives and nearly 100 false positives, those false alarms, from a state-of-the-art static analysis tool. This represents a significant reduction in the amount of manual effort that a developer would need to spend to review what a tool claimed were vulnerabilities, but were not in fact. Not only does RIVULET save developers time by having no false positives, it also completed its analysis task faster than the static tool. We also applied RIVULET to the test suites of 3 open source web apps and found 6 new vulnerabilities, and also showed that we could use RIVULET to reveal the Equifax vulnerability in struts. My research arc has come a very long way since GenSpace. I feel like hopefully I've done my best to make a timeline of the projects that I've worked on and the people most influential in pushing and supporting me down each of these arcs. There's one thing that I can leave you with, that research is an immensely collaborative process. It's not just the people at your school, but it's the people that you sit next to on a minibus ride at a conference, the attendees at the workshop that you happen to present a poster at, and who you hang out with at a coffee break. It's the community that you're a part of. So one last time, to Gail, Darko, Roxana, all of the faculty at Columbia that pushed me along through my studies, to my students, to my colleagues, and to all of you, thank you for your support, and thank you for this recognition. I hope to see you at the Ask Me Anything.